Okay, what we're gonna do today or this week, we're gonna really try to solve some problems applying the reliability method, first order the reliability method, and Professor Du's notes show 3 different nice problem sets. But you can find quite more if you look at the choice book also. And whenever you tap in, there is usually 99% is a first order, the reliability method, because second order, I'm going to introduce a little bit as Professor Du's note shows. So all this problem, 3 problem, we'll solve the first problem together. And second problem is also 2 random variable problem, but difficulty arises that you have to automate. So when you say you have to automate, you can just do it by hand. It's too many iterations. So second problem, we're gonna go through a couple iterations to understand the process. Then we'll stop. You have to do more iteration to get the MPP. So then that point, I want you to do as a project, group project. So 3 of you are each group, and I'm going to assign it. You have to start setting up, but you have to put quite a effort to program. Maybe some of you has experience, some of you don't. And third problem, as you might see, that's a 20 random variable. it's almost impossible by doing using your own hand and calculator, because you have to iterate something like 100 iterations. So many random variables. So that's why you can use MATLAB. I think all of you knows MATLAB. So that's what we have to use it. And thus this week, like a Friday, I'm going to introduce a Monte Carlo simulation, which is really more approximation, because difficulties arises then Monte Carlo method is somewhat nicer, but there is of course a drawback. You have to have many triers. It's not a one or two. So first it is developed in Monte Carlo, Monaco, which is really gambling country. Small city is a country near Italy, west of Italy. So 1940s, couple guys developed a technique to win the games, to make money in the game. That's what happened. So I'm going to introduce Monte Carlo method. Monte Carlo maybe next week. There's another simple, there are tons of different methods I mentioned to you in the reliability calculation. Another simplest method developed was so-called mean value first order reliability method, which is somewhat easier because you don't have to make a transformation. The reason we are using transformation here is really transfer into the standard normal distribution function approach. So it's at the beginning, road is really wide, then narrow down to restricting, saying that we want to get into the track, then that makes computation easier. So transformation from X space to U space, right? Then everything is fit nicely. All the projection of contour line is circle rather than weird shape. That makes it very simple. So, but this mean value method is, well, wait a minute, we may not need to make a transformation. Let's work directly on X space. It's something like solving the simultaneous equations of motions, saying that, okay, equations are all coupled. Why not just solving coupled the equations of motion directly? Maybe just one at a time, keep iterate. So it's kind of that approach is someone proposed. Then when there is a higher nonlinearity, of course, is not working well. But you could recognize pretty easily. And of course, you can compare the result as a trier, first with the transformation, or first by mean value approach, then use a different approach. So like a Monte Carlo simulation, then then you could say, wow, this is not working well. So such a things you can discover. But first, this week, I want to fully understand, then you can program, then solve second problem by programming, then third example problem set I really wanted to solve as a project, like a weekly project. We don't have much time giving you bi-weekly project, so we can solve using maximum a week. And sometime next week I want to, as a group, come out and show how you did it. Because each group, the way each group could do may be different. You can make it different. Some could go a long way, some could go much shorter way, okay? Then this week I really, after we solve example problem set, then I want to really assign the term project. Okay, that's the last. Depend on your performance on the term project. Depend on your performance of term project. I'll give you, of course, final exam. Maybe eliminate final exam, but just giving the replace to your term project. Really, if you demonstrate first order, I'm not going to go into second order, first order reliability method, and you develop the engineering problem with experience through example problem in your area. All of you working in the sort of the research project. So if you first discuss within the group, then generate the problem set, then you can come out, really give a short brief, like 5 to 10 minutes brief. Then I'll judge whether it's acceptable or not. If it's too simple, it's not the term project. So has to have a degree of practicality, you know, some meaningfulness on that. Then you can start working on the project. Then may take 2 weeks. 16 is the last week of a lecture, or 22nd is not the last week of lecture. Anybody remember 16? Friday? Aline, you know? So nobody cares? Wednesday is what day? 14 is the last day of lecture, so not much time. So, but exam starts the very next week, right? But really, I don't much care. So at least to finish term project, then I want you to really present, each group present, and you have to clearly show your own contribution. Among the three, one person can do everything, the other two are sitting, enjoy, have a beer, coffee, which is not fair. So that's what we're gonna do. That's the plan, okay? So next week or this Friday latest, I'm gonna really go through the mean value approach, which is very straightforward, but somewhat elegant, but there is no guarantee on stability. Explicit integration scheme in FEM, no guarantee on the convergence. But it's really nice and beautiful approach. Then how do I know whether the final result is has a converged solution. How? You have experience, explicit integration scheme. As you iterate, it's just to blow out the result so quickly and result in nonsense. 10 to the minus 10 to the 40 power, for example. Then you know it's the end of it. So you can really see such a situation somewhat clearly, but as you solve a little bit more problem, that's all you can do. Okay, the two equations that we discussed last week, the recursive formula is a beta. So beta value we have to keep iterate. What's the beta value? Physically, what does it mean? Ilyong, what does it mean? What's the meaningfulness of beta value? Beta value is the distance between origin to MPP. That's what you are really marching for, to iterate down to MP point, most probable point. And once you get that, so the UK plus 1 U, you have to iterate down to MPP point, really. This is simply distance, right? And you have to multiply beta to A. So by looking at this, not still clear, but when you do the example problem, it's going to be very clear. Multiple dimensional, of course, problem. A is a vector which has n different the random variable. And of course, beta is here, so I just put that in. Then you have to keep iterate. Then you have to apply the stop criteria, whether the result at the k plus 1 step or new step is converged to the older step. Then convergence can be applied to U or gradient G. This gradient G, what does it mean? Gradient G. Gradient G is gradient of the G function. G function is like this, G function. Then this is, if this is a point to U, this is G delta GU. Of course, there's a vector if you have n different dimension for the random variable. And again, another criteria you can use is beta could converge itself, right? K plus 1 is almost the same as beta k. Then you can stop. Epsilon 1, 2, 3, you can pick out the very small number. Or there is a different ways you can do, and you can normalize this guy. UK plus 1 minus UK divided by UK. Then you can assign the value, the epsilon, saying this is small enough, then stop, vice versa. Okay, so let's solve a simple problem first. question. But so far it should be clear. So first, let's say when we deal with two-dimensional random variable, and we assigned like R, right? We assigned as a S, example, and R is saying that this is like, what do you call this? R is a strength or yield stress, right? Or strength, or some other time we use yield stress. And S is, we use sometimes the word load or loading, and sometimes we use applied stress. It's all same. And then this is random variable. If you use this as a random variable, we have to assign the value describing the property of the random variable. The first one is a mean and the standard deviation, but I'm going to assign n, which is a normal distribution function. we're going to limit ourselves, the random variables are normal. Otherwise, you have to use a different technique like Monte Carlo simulations. The professor do kind of mention you could do it, but in the lecture I don't want to say you could do it. That's not a good idea. Assume here is a normal. Okay? So if it's a normal, and another thing is, assumption is what? Independent. Independent random variable. To make life easier, but I'll comment on the correlated situation. Just a comment. Okay, so here I'm going to say 200 and 20. The unit is megapascal, and this is 150, and this is 10. So this is mean, and this is standard deviation. So that standard deviation is a 20 for yield stress. Makes sense, okay? And for applied stress for the loading is concerned, is going to be the 10. First, this is all for given problem. And the performance function g x is equal to x1 minus x2. So here is use x1 and x2. In reality, it's like the strength and the load for engineering sense, okay? Two random variable problem. You can do by hand nicely in this particular problem, but even two random sometimes has difficulties in there. And first to define the limit state function or performance functions. Then next for transformation, x into the U space. That's what we have done it. So here, so in the transformation, which is equal to x minus mu x sigma x, then you put that in the standard normal distribution form. So here, this is x is equal to mu x plus sigma x u. So we're going to do the same way. So then gx is now x1. x1 is, of course, is x1 is equal to mu x1 plus sigma x1 u1. x2 is equal to mu x2 plus sigma x2 u2. Transformation from x space to U space. So here this is x1 minus x2. Then you replace this x1, x2 by this 2. If you do that, then mu1, I'm going to replace just the mu x1 as mu1. It's okay to simplify it. So sigma 1 u1. So nothing to confuse, just simplifies it. And minus mu 2 plus sigma 2 u2. Then we can just put the value. So mu1 is 200 megapascal plus sigma 1 is 20 u1 minus mu2 is 150 plus sigma 2 is 10 u2. So this is equal to 50, this guy, that guy, plus 20 u1 minus 10 u2. This is a performance function. A performance function now getting into the U space. It's a linear function. It's very nice, right? Then I can draw it. This is 0, this is u1, this is u2. You can plot that function here. Yeah. Well, you have to put something like g function. So you have 50 plus 20 u1, 10 u2 is equal to 0. When u2 is equal to 0, when u2 is equal to 0, right? If this is 0, U1 is equal to minus 2.5, right? So you have to put the tick mark like minus 1, 2.5. So line, the performance function should pass that point. Then you can do the slope. Yeah. Or you can just make another one. You set the U1. If this is U1 is equal to 0, what happens? U2 is equal to 5.5. That means passes here. So you draw, this is a performance function is a straight line. In this case, doesn't have to be straight line. It usually generates the failure surface. This is a G U is equal to 0. And the slope U1, U2, if you do, is 1 over 1 to 2 ratio. Okay, so graphically speaking, you can get the beta right away by looking, just by looking, without any iteration. So you are looking for, this is origin, and the distance from here to here is a beta. Graphically, you can see easily for 2D problem. For such a linear performance function situation, then here, what do you call the vector pointing this direction, which is equal to minus A. A, not minus A. In the gradient direction, this is G. And okay, well, let's continue. So, so this point over here, this point is, what do you call? What do you call that point? That's an MP point, most probable point. So that's what we're gonna calculate by the iteration. So in MPP algorithm, in the dude's handout, or I send you my lecture note for convenience. So MPP search, we have to get the search algorithm. Whether this is a 2D problem, 3D problem, approach is the same. First, if you look at the flow chart, there's first is initial starting point. Always has to start someplace, but this is just the approach. This doesn't have to be 0, 0, but usually this is good idea for reliability path search, because you're dealing with a beta or U star from the origin, rather than pick out some place and going down near the 0 point. Might be a good idea. Start from the origin for trier. the vector u. So here is, you may start any place you want, but this is beginning. So the initial starting point somewhere on the u, because we don't know. And the 2, so now beta is a norm of the u, because this distance is equal to distance u. Okay. Beta 0 is equal to the distance is u1 squared plus u2 squared. Beta is a norm, right? What's the value? Ilium. It's there. What's the value? 0. Because initial trier is 0. This is 0. When you program, you will start, you have to assume initial vector u naught 0 vector. Next is to compute the A. A is correctly speaking, that should be a u star, and the norm of the u star. So this quantity you have to compute, that quantity you have to compute. Then you can compute the A naught. If you compute the A naught, then you can compute the that portions, things like that. You can, this relate right there. So gradient G u, first trier was u naught. This gradient is G u delta del u1 del G u del u2 right at the u naught. So ug over del G over del u1, del G over del u1, what's the value? So 20, right? And next, del G over del u2 is minus 10. So this gradient component is 20 minus 10. Next is you have to find this systematic is equal to what? Yunso, what's this? Look at me, not there. What's this? Norm. Norm is 20 square, this guy, plus 10 square, right? Makes sense? Then this value is 22.36. Everything here, the unit should be what? Megapascal. You could write at the beginning or anywhere you want, saying this is unit is so and so. Okay, so now we get this component. So here I'm going to replace proper. This is not yet U star. It's gonna be like this. Then if it's a U naught, this should be A naught. Okay. So then you can get the A naught. How many components do you expect for A naught? 2 components. U1, U2. So this is that component here. That first component is 20 over 22.3607. The other component is minus 10 there. This guy is 22.36. Max, the number of digit to carry below the decimal, usually 4 places should be good enough for engineering calculation. Sometimes 2 places may not be that good. So any calculation we do, let's limit to 4 places below the decimal point. Okay. So if you do this, this is 0.8944 minus 0.4472. Pretty systematic. For programming, it shouldn't be that bad. You could do very systematic. Okay. If you solve a couple problems, then you will get your own idea. So what's the next step now? This is 3. What's the next step? Now you are really ready to get into recursive mode for beta. So we're gonna getting into the first beta 1, first iterations, right? So we have beta, we're getting into the beta naught. So we're gonna getting into 1, beta 0, then this is, we know, we just compute this, U naught. This is delta G U naught. So we have all the information, do we? Answer is yes, we have. So this guy, delta G U naught, what's the value? What's the G value for U naught equal to 0, 0? What's this value? I'm sorry. This is, we need you say, hey, Professor Shin, you made a mistake, but you keep doing it. We'll sit back, enjoy. It's not true. This is G. This is G, right? Okay. So G is equal to, if you replace U1, U2 as a 0, 0, then you will have G at U0 is equal to 50, right? No? G is equal to 50, right? Plus 20 U1 minus, is it correct? 20 minus, right? Then when this guy is G U0, which is 0, 0, which is equal to 50, and this guy is equal to 50. Okay, so now this guy is 50. What's this guy? This is a length, right? Known 22 point over there, 3607, right? So what's the beta naught there? 0. So now if you do that, this is equal to 2.23601. This is the what? The distance from here to here. So step 5. So now U1 is equal to minus A0. One step below, we don't know A0, A1 yet, so we use the 1 for previous. So so U1 is equal to minus, what's the A0 over there? 0.8944 comma minus 0.4472 times beta 1 is 2.2361. If you compute that, this is minus 2, 1. What does it mean graphically is this point, minus 2 dash 1. You can compute, by line equations. So, but anyways, the iteration process is what you have to go through. So it's minus 2. It's one iteration, linear performance function situations. And now, not the final step, you could go back and compare the two values for the U or beta, or gradient vector. But if I compute the PF, PF is equal to P minus beta. Beta is right there. P minus 2.2361. You can compute in the MATLAB, or you can look at the standard table, right? You know how to use that. Standard table, 0.0127. So it's minus value. Minus, this is minus 2.2361. So you're talking PF is this area is what the PF is. So this. Then what you're gonna do? You can compute the mean value and standard deviations. You can compute the mean of G mu1 minus mu2 is 50. Make sense? Make sense? Because in the U space, mean is equal to 0. Then this is mean of G, performance function. Sigma G. You can use a square to get the variance, but mean, the standard deviation is the square of each component is equal to square 7. One thing here, if a function is equal to A0 plus summation of C AI what's mu y? In other words, EY, you know all this, of course, plus U space I'm talking. We are working on the U space. The U space. So one thing I want to show you here is this is a constant, right? What's the E of the constant? Which is A9. That's what I want to tell you. What about sigma y square for this case? Then what you involved is sometimes I feel sometimes it's confusing. Sigma, let's use the variance here. Square root of the variance is the standard deviation. If you first term, if you take variance of A0, what's the result? 성태. Say 0. Sigma over variance is the random variable minus mean square. You can visualize square. And what's the variance of, by looking at the probability function, if it has a spread, it has a variance because there's a dispersion, measure of dispersion. Common sense first. If, then of course this is non-zero, sigma you have a variance. But what happens if you have a stick out like that? Constant. What's the, I'm asking you a stupid question. What's the value of uncertainty for such a spike? There's no uncertainty in there. Don't look at me like that. This is zero. Simply just a common sense. Or 0 minus 0 squared. Then take a mean of 0, which is 0. Then is equal to, constant is equal to 0. Things like that. I want you to review quickly as we're going into reliability method, then forgetting what we did for basic definitions of statistical property. That's natural. That's what all the human beings, you know, sometimes a lot of things are bothering you in the past, but as time goes by, it's forgetting. In Nonsan training camp, when I was there many, many years ago, you know, that leader used kokgengi, which is really long wooden pole, just hitting our back. That time I remember his face for years, you know. And after that, forgetting. Otherwise, we can't live. So forgetting is natural process, but you have to go back once in a while to understand. And I know you have a class coming up, another class coming up. I have to put this last sentence, last word here. So here is a sigma line that PF is equal to probability GX less than equal to 0, then phi is 0 minus mu g over sigma g, which is equal to phi 0 minus 50 over 22.3607, then which happened to be phi minus 2.2361. Okay, then that happened to be 0.0127. This is identical to what we have before. You may not need iteration, but for practice you can iterate once again as you wish. Okay, that's the end of it. Example problem number 1, very straightforward. Process is identical. So tomorrow, Wednesday, I'm going to do a second problem. I'm going to bring some other problem. Then you can do it at home. Practice it. That's what we're going to do. Then Friday, at least the Friday morning or Wednesday, I have to assign the homework problem to start the building up your own program. And we're going into mean value approach. Question? I think it's clear. Sorry, I know time, I should have quit a few minutes earlier. I want to finish up to this point. So I'll see you Wednesday. Okay.